This is chapter 12, lesson 3 on matrix operations. All right, so now we're going to add and subtract, and we're going to multiply matrices by one individual number and multiply multiple matrices. All right, but first we have to consider. Let's look at the dimensions of a matrix. So if you're with me on page 804, so look at matrix A. It's 3, 2, negative 5, 6, 1, 7, negative 2, 0, 5. And B matrix is 3 halves, negative 5, 0, and 12. So what are the dimensions of these matrices? It's always row by column. The number of rows by the number of columns. So this would be a 3 by 3. All right? And this would be a 4 by 1. So in order to add or subtract a matrix, they must have the exact same dimensions. So if I have a 3 by 3, in order to add or subtract another matrix, it has to be a 3 by 3. All right, so adding and subtracting, the matrices must have the exact same dimensions. So look at example 1. A is a 3 by 3, and B is a 3 by 3. All right, when I have a 3 by 3 and a 3 by 3, I can add or subtract them. And all that I'm doing is, all right, so this is row 1, row 2, row 3, right? This is column 1, column 2, column 3. All right, so all we're doing is we're going to add from matrix A, row 1, column 1, to row 1, column 1 of matrix B, all right? So we're adding each place, row 1, column 1 to row 1, column 1, row 1, column 2 to row 1, column 2 of the other matrix, all right? So we're going to add 3 and 5, that would be 8. Subtraction is the same way. 2 and negative 6 is negative 4. Negative 5 and 2 is negative 3. This is what A plus B looks like. All right, 6 plus 4 is 10. 1 plus 5 is 6. 7 plus negative 4 is 3. Negative 2 plus 1, negative 1. 0 plus negative 1, negative 1. 5 plus 0, 5. And subtraction would be the exact same way. You would do 3 minus 5. I could do A minus B, or I could do B minus A, right? 3 minus 5 would be negative 2, right? And you can follow through that example in your textbook, all right? Now, in order to multiply, the first thing we're going to look at is called scalar multiplication. That is taking one value and multiplying it by a one single value. So we're going to leave matrix A on the board. And example 2 is just asking us to find 3A. And all that means is I'm multiplying 3 by every term in the matrix. So I take 3 times 3 is 9. 3 times 2, 6. 3 times negative 5, negative 15. 3 times 6, 18. 3 times 1, 3. 3 times 7, 21. 3 times -2, -6, 3 times 0, 0, 3 times 5, 15. So scalar multiplication can be used with any dimension matrix. It doesn't matter, right? Now matrix multiplication is different. So I want us to first, let's go ahead and look at example 3, and I'm going to help you understand when you can multiply matrices, all right, matrices. You have to, the dimensions matter. Not every 2 set of matrices can be multiplied. All right, so I'm going to write them down. Okay, so when we look at whether or not we can multiply a matrix, we're going to look at what matrix, I'm just going to put row by column, right? Their dimensions, okay? And another matrix, we look at their rows by columns. All right? You can only multiply matrices if these 2 values are the same. So the columns, the number of columns on the first matrix must equal the number of rows on the second matrix. All right? And what the result is going to be, the dimensions of the matrix, once we multiply it, is going to be the number of rows from the first one and the number of columns from the second one. This will be what the dimensions of what A times B looks like, okay? All right, so first we have to ask ourselves, can we multiply the matrices? And then we must be aware of what will the resultant matrix look like, all right? So let's look at the dimensions of these 3 matrices. All right, so rows by column. This is a 2 by 3. B is a 3 by 2. And C is a 2 by 2. All right, so let's ask ourselves, can we multiply A times B? All right, A is a 2 by 3, B is a 3 by 2. They are the same. So we can, the columns equal the rows, columns of the first equal the rows of the second. We can. What will the resultant matrix look like? It'll look like a 2 by 2. All right, so we're going to come back and work A times B. We can do that. All right, so that one works. Can I multiply A times C? A is a 2 by 3. C is a 2 by 2. They are not the same. We cannot multiply them. So that one will not work. All right. Can I multiply B times C? B is a 3 by 2. C is a 2 by 2. That works. Can you see that? That works. And what will the resultant matrix be? It'll be a 3 by 2. So we can multiply B times C. All right, so let's look at these a few other ways. Can I multiply B times A? All right, so B is a 3 by 2, and A is a 2 by 3. Look here. Yes, we can. Those equal, but the resultant matrix will be a 3 by 3. It's different multiplying A times B then multiplying B times A. All right? All right, so hopefully you see that. So what do we do when we multiply? This is what we do. It's the sum, so that's the word of the sum, of the product of A's row 1 times B's column 1. All in this first position is the sum of each position in this row multiplied by each position in this column. All right, so let's just do it. It just helps just to do it. We're going to multiply A times B. All right, so this is going to be pretty big. I'm going to erase this because we're going to just see what each position looks like. Okay, this is going to be my first position. It's going to be 3 times 2 plus 1 times 0 plus 2 times 1. That's all in my first position. All right, we do row 1, column 1. Then we do row 1, column 2, and that goes here. Okay, first row, second column. All right, remember we said we were going to have a 2 by 2. Let's just prove it. So in the second position here, it'll be 3 times -3 plus 1 times 5 plus 2 times 8. All right, I just took this row, multiplied it by this column, then I took this row, multiplied it by this column. We'll do the math in just a minute. Probably don't need to be that low, huh? It's just going to be a 2 by 2. All right, now I'm going to take row 2 and multiply it by column 1. All right, so that's -1 times 2 plus 0 times 0 plus 4 times 1. That's row 2, column 1. And look at the position it's in. It's in row 2, column 1. All right, now I'm going to take row 2 and multiply it by column 2. So it's -1 times -3 plus 0 times 5 plus 4 times 8. All right, so we'll try to, that's going to be 0. That's 6 plus 2 is 8. I'm just going to get my calculator just in case I need it. Then we have -9. I'm going to use it now. -9 plus 5 plus 16. And this position will be 12. That's -2. That's 0. -2 plus 4 is 2. And that's 3. That's going to be 0. 3 plus 32 is 35. So that's what A times B looks like. All right. Now, let's do B times A to see what that would look like. All right, so this is A times B. Now, when we do B times A, remember, we're going to take row 1 of B, multiply it by column 1 of A. So we're expecting a 3 by 3, all right? So row 1 times column 1. That's 2 times 3 plus -3 times -1. All right, I'm going to stay on row 1, multiply it by column 2. All right, so that's 2 times 1 plus -3 times 0. You with me so far? Now I'm going to go to column 3. It's row 1 times column 3. And that's 2 times 2 plus -3 times 4. All right, now I'm going to go to row 2 and multiply it by each column. All right, this first one's always going to be 0 because 0 times anything is 0. So I'm just going to multiply by 5. So it'd be 5 times negative 1 is negative 5. 0 times 1 plus 0 times 5, that's just 0. 0 times 2 is 0. 4 times 5 is 20. Make sense? Then the third column. I'm going to multiply the third row. We'll go to the first column first. So it's 3 times 1 plus 8 times negative 1. Second row is just going to be, second column, 1 times 1 and 0 times 8. So that's going to be 1. Third column is going to be 1 times 2 plus 8 times 4. All right, so what will be A look like? That's 6 plus 3 is 9. 2 plus 0 is 2. That's 4 minus 12 is going to be negative 8. Then we have our second row. I need to move this down a little bit, don't I? Second row, negative 5, 0, 20. And then we have 3 minus 8, which would be negative 5. The 1 is there. That's 32 plus 2. That's 34. So B times A is, in fact, a 3 by 3 matrix. All right. Example 4 on page 808 is a practical example. It's a word problem of a matrix. And you do the exact same thing if you are multiplying. But we're going to do this one in our calculators. All right? So, if you will go into matrix, and let's go in and put in the first matrix, the hours, okay? So it is a 3 by 3. So I'm entering that in matrix 1, a 3 by 3, and I'm entering 0.5, 2.5, 1. 1, second row, 4, 1.5, third row, 3, 7, 4.5, okay? So I have my first matrix entered in matrix A. Now I'm going to quit out of that, and I'm going to go back to matrix, and I'm going to enter the cost per hour as matrix B. And it is a 3 by 1. And so we'll enter 7, 18, and 10. And this is matrix B. So I'm going to quit out of that. Now I'm just going to multiply them on my calculator. So from your calculating screen, you go in, back to matrix, and you just hit enter on matrix A. And you'll get matrix A. Then you multiply, just hit the multiplication button. Then go back in to your matrix and choose matrix B. And hit enter, and B pops up. And then when you hit enter again, it multiplies them. And it gives you the answer. Okay? So you can do that in your calculator. Of course, you can add in your calculator too, but it's important that you need to know, can I multiply and how do I add? All right? Now, directed networks. What in the world is a directed network? I'm going to draw the picture of the network that is on page 809. All right, I'll do the best I can. L, M, and K represent vertices. All right. So I'll start at L down here. And L goes up to K. And we'll say M is about right here. And M goes up to K. L and M have arrows on both sides. M goes back down to L, and then at M we have this circular. All right, so when do we use directed networks? I think of the network, the worldwide. It's a web. It's sort of like a web. So it's used practically. Its practical applications are like the web. All right. So let's just look at what happens here. This is called a directed network, and we can establish a matrix from this, and it would be called an adjacency matrix. These are one-stage pathways. All right. So let's look at the pathways. L goes to K, right? L goes to M, and that's it. K doesn't go to either L or M because all of the arrows are pointed towards K. So nothing leaves K and goes to L or M, okay? You can also think of, I just thought of that, airports and how they plan flight paths, all right? All right, so nothing leaves from K and goes anywhere. But L goes to K, M goes to K. Oh, there was another one, wasn't it? And there we go. All right. All right, I forgot that one, sorry. And L also goes to K. Look, L goes to K in two paths. L goes to K here, L goes to K there. So there are actually two paths from L to K. From M to K, there's only one path. All right, look, L not only goes to M, but M also goes to L. There are two paths from M to L, here and here. And M also goes back to itself. So if we were writing this in a matrix, K, L, M, this is from. Is it coming from here? And then we would write K, L, M. Is it going to these places? Okay? All right. So looking at this matrix, does K go to K? K does not go to K. See, this is like M going to M. So there are 0 paths from K to K. Actually, there are 0 paths from K to anybody, right? So K doesn't go to L, K doesn't go to M. All right, now look, L to K. Remember, we just said there are 2 paths. There's 1 path to K, 2 paths to K from L. All right, and does L go to L? L doesn't go to L like M goes to M. So there are 0 paths from L to L. What about L to M? L to M, there's just 1 path from L to M. All right, what about M to K? That'd be M to K. There's only 1 path from M to K. Only 1. What about M to L? Remember we said there are 2 paths. M goes to L here and M goes to L there. And M to M, there's 1 path. All right, so for a directed network, you simply need to be able to establish an augmented matrix to show the path. And you just use the arrows, right, to determine where do we go from to. What are the paths from the vertices to the vertices? That's it for this lesson.